All right, so let's continue with a few more examples of supremum and infimum, which now can include plus and minus infinity. And the first example that I want to do, I want to show that infimum of a set of all numbers that look like minus natural number cubed, that the infimum of a set like that is going to be minus infinity. So we're going to try to satisfy the definition of infimum being equal to minus infinity. And remember that we said that, so let's just recall it here. So recall, infimum of S is equal to minus infinity if for any m less than 0, there exists an element of your set such that the element of a set is less than m, right? So capital M cannot be a lower bound because we found an element which is lower than that capital M. And if this is true for all capital M, then of course there is no lower bound, so that means that the set is not bounded from below, so it is its infimum is minus infinity. Okay, so now choose any m less than 0, and I want to verify that I should be able to find this element S, which is below m. Okay, so then I'm going to consider two numbers. Last time when I used a similar example, remember that we used Archimedean properties, so I'm going to try to do it again. But in order to use Archimedean property, I need to have two positive numbers. And right now I have a negative number, single negative number, capital M. So I'm going to consider two numbers, minus m and 1. Then both minus m and 1 are greater than 0. So then by Archimedean property, I can conclude that there exists an n, which is a natural number, such that n times 1 is going to be bigger than minus m, right? Or that is the same thing, minus n is bigger than minus m. Okay, so n is bigger than minus m. N is a natural number. Well, then what will happen if I cube that natural number? Since n is greater or equal than 1, right? Then if I take n greater or equal than 1, so again, let's try to do it more carefully here. Later on, we will do this. We will skip steps when we show do similar computations. So if n is greater or equal than 1, if I multiply both sides of this equation by n, then I'll have n squared is greater or equal than n, right? I can multiply both sides by n because n is a positive number. It's a positive integer. So n squared is greater or equal than n, but then n is greater or equal than 1, right? So again, take this inequality, multiply both sides by n, you get this inequality. But then I can combine it again with inequality here, n is greater or equal than 1, and so therefore n squared is greater or equal than 1. So then I do this again, multiply both sides of this new inequality that I got by n. I'll have that n cubed is greater or equal than n. Combining this again with n greater or equal than 1 gives me n cubed greater or equal than 1. Right, so if we appeal to the properties of the ordered field, right, then by using these properties, I can immediately demonstrate that n cubed must be greater or equal than 1. Sorry, not greater or equal than, actually, yeah, I don't need that. Sorry. So this will go away. What I need is that n cubed is greater or equal than n. So if I have n cubed greater or equal than n, then we can combine this with, let's see, with this expression. This will imply that n cubed, right, so n cubed is greater or equal than n is bigger than capital M, so transitivity of ordering means that n cubed actually is greater than m, right? So once again, I take this inequality that I proved, n cubed is greater or equal than n. I take inequality n is bigger than m. I combine them together, n cubed greater or equal than n, which in turn is greater than m. And so in that would imply that n cubed is larger than m. All right, so we proved that I can find an integer, positive integer n, such that n cubed is greater than capital minus capital M. Sorry, again, I'm missing stuff, but right, so n was bigger than minus m. That's because that is actually our inequality. So again, capital M was a negative number, minus m is a positive number, so I'm able to find n cubed, which is larger than minus m. Okay, so then from that I can conclude that if I multiply both sides by minus 1, then one of the properties of ordering that we proved in the theorem, I believe 3.2, was that if we multiply both sides by minus 1, then the sign of the inequality will change. So then what I get is that minus n cubed must be less than m. Okay, but then how is minus n cubed related to minus n cubed? Can I move minus sign inside cube? Right, we know that we can do that. So we get minus n cubed less than m. Okay, but then how was our set S defined? Set S is defined as any number which is negative n cubed when n is in n is a natural number. So then we're done, because I was able to find such an n, right? Because minus n cubed, number minus n cubed, is an element of my set S. Right? So we proved that the intimum is minus n the all right. So let's do another example. Let's suppose, or actually let's do this. Show that for S equal to, let's say, set S equal to a square root of n, where n is, again, an element of a set of natural numbers, that for it we have infimum of S is equal to 1, and the supremum of S is infinity. How would we prove that? So let's do the infimum first. So for the infimum, right, I need to demonstrate that 1 is the greatest lower bound, right? So by definition of S, what are the elements of my set? They're square root of n, right? So if I take a square root of any natural number, it must be greater or equal than 1, right? So if square root of n is greater or equal than 1, then what I have is that 1 is a lower bound on S, right? So again, for any natural number n, so n square root of n is greater or equal than 1, for any n in n, since for any natural number this is true, then from the way I defined S, square root of n must always exceed 1, so 1 must be a lower bound on S. So B, I need to prove that 1 is the greatest lower bound. And so that what we do next, I'm going to choose any, let's say, any t, which is greater than 1, right? So what I want to show is that t cannot be the lower bound, right? Because otherwise, if t was a lower bound, then 1 cannot be the greatest lower bound. So I choose any t greater than 1. Then, what can I observe here? So why t cannot be a lower bound? Because I should be able to find an element of my set which is below that t, right? So if I can find an element of my set below t, then t cannot be a lower bound. Why should I be able to find such a set? Well, so we can immediately note one thing, that, so let's write it as a note, that 1 belongs to the set S, right? Because when n is equal to 1, 1 is a natural number, square root of 1 is 1, so 1 belongs to S, so therefore there is an element of S below T. And so therefore T is not a lower bound for S. And so therefore any number greater than 1 is not a lower bound. 1 itself is a lower bound. So then we conclude immediately from this that the infimum of S is equal to 1. Let's modify that. All right, so that is the first part of the proof. In the second part, we want to show that the supremum is equal to infinity. So B, I want to show that supremum of S is infinity. Well, so again, to show that supremum is equal to infinity, I have to demonstrate that S is not bounded from above, which means that for any positive number, I should be able to find an element of my set which is greater than that number. So choose any positive M, then by Archimedean property for 1 and M, there exists a natural number n such that n times 1 is bigger than m, right? So if there exists such a number, then clearly, if I take, let's see, what are we trying to do? We're trying to show that square root of n is bigger than m. So let's actually modify this a little bit. Tiny little bit. So I'm going to use Archimedean property not for 1 and m, but for 1 and m squared. So fine. So in that case, still, there exists an n such that n times 1 is bigger than m squared, right? Because I can use Archimedean property for any two positive numbers. Okay, so but then if that is true, by taking square root of both sides, I'll get that square root of n is bigger than square root of m squared. Square root of m squared is absolute value of m, but m is positive, so absolute value of m is m itself. So, what have I been able to show? My set capital S consists of everybody who looks like a square root of a natural number. So, what I was able to find is that there is an element of my set S, which is the square root of this n that was given to me by the Archimedean property, and square root of n is bigger than m. And so that means that I'm done. So, conclusion is there exists an element of S capital S which is larger than m. And because this is true for any m, then I'm done. Then that my set is not bounded from above, and therefore the supremum is equal to plus infinity. Next, I want to talk about a couple more results. So I think this would be number 6. And that does not necessarily, that's not going to necessarily refer to the case when the supremum was equal to infinity. So the next two results are going to be true regardless of what supremum and infimum of your set are. So let's suppose that I have two sets. S is a subset of T. So then, supremum of S is going to be less or equal than the supremum of T, and the infimum of S is going to be greater or equal than the infimum of T. This is probably clear, but let's try to prove this nevertheless. And the proof is going to be really short. So for every T in T, we have that T is less or equal than the supremum of T. In particular, if the set T is unbounded from above, right, then T must be unbounded, right? So then T can be a number which is arbitrarily large, but it's still going to be less than infinity, which is a supreme. So then this is true because supremum of T is an upper bound on T. Okay, but then because S is a subset of T, right? Every element of S is still an element of T. We then have that S must be less or equal to the supremum of T for every S in S, right? Because an element of S is still an element of T, and supremum of capital T is an upper bound on capital T, so it's still an upper bound on S. Okay, so that means precisely what I just said. So sup of T is an upper bound on S. Now, at the same time, what is supremum of S? Supremum of S is the least upper bound on S. And so then if I have two upper bounds, one is the least upper bound and another one is just an upper bound, that means that the least upper bound, which is supremum of S, must be less or equal than just an arbitrary upper bound, which is the supremum of T. So therefore, sup S is less or equal than sup of T. And the proof of inf of S greater or equal than inf of T is similar. Right, you just have to replace words upper with lower and less or equal with greater or equal. I encourage you actually to verify that. So that means that if we have a set and we make it larger, that means that we're allowing supremum to grow and infimum to decrease. Okay, so now I'm going to use this fact to prove the next theorem. And the next theorem, let's write it as a statement number 7. So I'm going to suppose that the sets A and B are non-empty. Then I'm going to define the set A plus B as a set of all sums of numbers x plus t, where S is an A and T is in B. Then we'll have that the supremum of A plus B must be the same as the supremum of A plus the supremum of B. And I'm not going to write this down, but for infima, exactly the same statement will be true, that infimum of A plus B is equal to the infimum of A plus infimum of B. And notice in this case, I'm not saying whether A or B are bounded from above or not, so that means that the suprema in principle can be equal to infinity. Okay, so proof. So the first thing I'm going to note that A and B being non-empty, this implies that supremum of A and supremum of B both cannot be equal to minus infinity. Right, because remember, if supremum is minus infinity, that means that your set does not contain any elements, because you cannot have numbers which are less than minus infinity. So that means that here, when I'm adding stuff, I will not be adding minus infinity to anything. So A, let's suppose that at least one of the sets A and B is not bounded from above. So in that case, in fact, let's do this. Without loss of generality, so whenever I write this WLOG, this is just a shorthand for saying without loss of generality, I'm going to assume that A is not bounded. Right, because likewise I can assume that B is not bounded, or both A and B are not bounded, but it's enough for me to just assume that A is not bounded. So if A is not bounded, then not bounded from above, sorry. Right, because that's what we're talking about here. From above. So then, if A is not bounded from above, that can be written as supremum of A is equal to infinity. So then, since and we really did not define that before, but this is sort of an obvious definition. Infinity plus any number, or infinity plus infinity is equal to infinity. We have that supremum of A plus supremum of B is going to be equal to infinity. right? So A here is any number. The only ambiguity that you might have is that if you add infinity to minus infinity, but we eliminated that possibility because the sets are not empty. Okay, so that means that the right-hand side of this expression will be infinity if supremum of A is infinity. Okay, so let's now look at the supremum of A plus B. So what I'm going to do, so now choose any B in B, right? And I can choose at least one element in B because B is not empty. And define the set A plus B as being a set of all elements of the form S plus B, where S is an element of A. Okay? So then I claim that A plus B is not bounded from above. So what I'll ask you to do is, on your own, prove this. So basically, if I have a set which is not bounded from above, and to all elements of that set I'm going to add the same number, then it must be true that a new set that you form this way is also not going to be bounded from above. So again, prove it on your own. So then, if I take a supremum of A plus this element B, that is going to be equal to infinity. Okay, so however, if I compare the sets now, A plus a single element B, and the set A plus B, which consists of all possible sums of elements from A and B, then A plus single B is going to be a subset of a set A plus all possible B's. And so therefore, by the previous example, which was, I believe, 6, what we have is that the supremum of A plus B, this guy is less or equal than supremum of A plus B. Well, but then I know that this supremum is equal to infinity. Supremum of capital A plus B is greater or equal than this number, so what is greater than infinity? It's only infinity. So supremum of A plus B is also equal infinity. Okay, so that is a proof for the case when at least one of the sets A and B is unbounded. Right, clearly I can do the same thing if B is unbounded instead of A, so then it's enough to just do it for A. So that proves the first part of the statement. Okay, so then if none of the sets is not bounded from above, so then the second possibility, which I'm going to list as B, so now suppose that both A and B are bounded. And again, bounded from above. Okay, so then by completeness axiom, supremum of A and supremum of B are finite numbers. And because supremum of A is an upper bound on capital A, then that means that if I choose any element of capital A, then that element must be less or equal than supremum of A. So this should be true. And likewise, supremum of B is an upper bound on B, so T is less or equal than supremum of B for all T in B. And so, if I choose any S in A and T in B, it follows that S plus T must be less or equal than supremum of A plus supremum of B, or what does it mean? If for any element of my set, so in this case an element is S plus T, it's less or equal than the same number, sup of A plus sup of B. That means that sup of A plus sup of B is actually an upper bound on A plus B. So that is sup A plus sup B is an upper bound on A plus B. All right, so I show that it's an upper bound. I also want to show that it's a least upper bound. So it remains to show that that same number is a least upper bound. On A plus B. Well, let's do that. So to demonstrate this, I'm going to note the following. If I have some number, epsilon, which is greater than 0, then, so then what do we have? If I take supremum of A and I subtract from that supremum epsilon over 2. Remember, right, that the supremum of A is the least upper bound on A. So then if it's the least upper bound on A, that means that if I reduce it by whatever amount I reduce it by, then the resulting number is not an upper bound on A, right? So let me move this here. This guy is not an upper bound on A. And because it's not an upper bound on A, What does it mean that something is not an upper bound? I should be then able to find an element of my set above this number. So there exists an S0 in A such that S0 is bigger than sup of A minus epsilon over 2. And now exactly the same thing would be true for B, right? Because, except I have to replace A's by B's. If I take sup of B minus epsilon over 2, sup of B is the least upper bound on B. I reduce it a little bit. The outcome is not an upper bound, so therefore I should be able to find an element of B which is above that number. So there exists now T0 that belongs to B such that T0 T0 is bigger than supremum of B minus epsilon over 2. Okay, so even if that is true, if I take then S0 plus T0, and by the way, S0 plus T0, S0 is in A, T0 is in B, so S0 plus T0 must be an element of A plus B, right? And S0 plus T0 is greater than sup of A minus epsilon over 2 plus sup of B minus epsilon over 2, right? Because individual S0 and T0 are bigger than these numbers. And if I add these, I'll get S0 plus T0 is greater than sup of A plus sup of B minus epsilon. And so the conclusion from this now remember that my number epsilon here is chosen arbitrarily, right? I just said epsilon is a positive number, any positive number whatsoever. So that means that supremum of A plus supremum of B minus epsilon is not an upper bound on A plus B, right? Because S0 plus T0 is an element of A plus B, and S0 plus T0 is greater than this number. So that means that sup A plus sup B cannot, minus epsilon, cannot be an upper bound on A plus B. And because epsilon was chosen arbitrarily, this should be true for any epsilon greater than 0. And so then what does that mean? Any number smaller than sup A plus sup B is not an upper bound, but sup A plus sup B is an upper bound, like we already showed. And so therefore, supremum of A plus B, the least upper bound on the set capital A plus capital B, must be supremum of A plus supremum of B, and we're done. All right, so that concludes this lecture, and I'll talk to you next time.